So let's get started. I would like to welcome everyone to our product showcase presentation, Comfort by Design, an introduction to VRF technology, organized by New York Task Force and presented by Mitsubishi Electric Drain USA, the largest manufacturer of VRF equipment nationwide. I would like to thank you guys, Mitsubishi Electric, for your support as a New York Task Force manufacturer member throughout the years. We will record the presentation and make the recording available on our website, nytaskforce.org, where you could also join us as a member and support our efforts like today. We will have a Q&A session at the end of the presentation, so please post your question into the chat box, and then Alec, myself, or Caleb will take them at the end. So it's my pleasure to welcome Alec Del Vecchio, Commercial AR Manager and Architectural Lead for Mitsubishi Electric. So please, Alec, take it away.
Awesome. Thank you, Andreas. First off, just want to say thank you guys for having me in here today. It's going to be a pleasure to get to speak to you guys. So this is just quickly going to be a kind of high-level overview of information on VRF systems, how they work, the components that they're really comprised of, best applications, and really how they can help you in your architectural designs and how they can be implemented into building projects. So without any further ado, I'm just going to get moving ahead. So as Andreas said earlier, this presentation is called Comfort by Design. It's an introduction into HVAC variable refrigerant flow, or VRF technology. Just quickly, I know this is a little bit of a word puzzle here, but we have to show this slide. This is just proving that this presentation is AIA accredited for all of those looking for credits after this presentation. So firstly, we are going to go into a high-level VRF technology overview, and the first topic we're going to cover is worldwide usage of variable refrigerant flow technology. So as you can see here, this first slide outlines the usage worldwide of VRF HVAC systems as opposed to more typical, we would consider HVAC systems here in the United States. As you can see in Japan, actually where VRF was invented, HVAC systems are 90% VRF. In China, it's a very similar number at 86%. In Europe, it's actually at 81%. So we may ask why this is the case, and we're going to look in a couple minutes as to the usage and the percentage usage in the United States. We'll take a look. I'm going to spoil the surprise for everybody. VRF usage in the United States is down at only 6% of total VRF systems installed. Why is this the case? Realistically, it's because in Japan, China, Europe, they have had to adhere to the much more stringent kind of green energy protocols that are going to be a little bit more commonplace in the United States. I'm sure a lot of you are aware of the local law 97 push going on in New York City and New York State as well. A lot of these other countries had to implement and adhere to those similar kind of standards for a long time. VRF equipment, as opposed to more typical HVAC systems that you see here in the United States, whether that be window units, rooftop units, chillers, movable units, HVAC systems are significantly more efficient, and that allows them to really kind of provide that heating and cooling that is going to be required in your application without kind of breaking the new kind of legislation that's going to be coming out. So just quickly, what is VRF technology? I know it's kind of a little bit of a mystery here in the United States as we just went over, but basically break it down into just three main components. So the first is going to be a compressorized outdoor unit. So this is going to be the unit that's going to be providing refrigerant to the system throughout your building or throughout your application. That refrigerant is going to be provided to all of your indoor units through flexible refrigerant line set, which is actually a very, very important thing to take into account. We're going to get into this more a little bit later down the line, but it's really good to know that VRF installation is extremely flexible and can be really kind of customized to the application that you are going to be working on. This is one of the main advantages for VRF over a lot of its competitive HVAC kind of technologies. So moving along, that flexible refrigerant line set is going to be tied into individual fan coil units in each zone. Now, this is not always going to be the case. that we're going to have an individual fan coil unit in every zone, but the way we like to think of VRF technology is as a zoned solution. We're going to get into a little bit more how that zoning works, how it can be applied further into the presentation. But one thing I want you guys to take away right off the bat is that VRF technology is about providing the correct amount of cooling or heating to satisfy the load in any given zone on your. So moving forward, there are two different kind of distinctive types of VRF heat pump technology, or sorry, VRF technology. The first one that we have is going to be heat pump technology. So the main thing to take into account is it's very similar to, you know, that picture we had just saw on the previous slide. You're going to have your outdoor unit, you're going to have your piping going to all of your indoor units. But the main difference between this and the technology we're going to get into next is it's going to act exactly like a 2 or 4 pipe hydronic system, where we're going to only be able to provide heating or cooling to all of the zones at any given time. So this system is going to act where all of your indoor units are going to be providing heating, or all of them are going to be providing cooling. One important caveat to this is that each individual zone can provide a different level of heating or cooling. So say you have one room that only requires a little bit of heat or a little bit of cooling, while another zone that may have a lot more occupancy or solar load is going to require more heating or cooling. That can be accommodated. But while that is the case, all of the units are going to need to be acting in the same mode at any given time. So this is a very common type of VRF technology. This was actually the first type introduced in the United States on a commercial level. This is great if you're working on somewhere like that's going to have a very kind of matched load profile. You're not going to see a lot of diversity in the space. This is good for schools or any kind of institutional building where they're used to that kind of 4-pipe changeover into heating or cooling. Luckily, with VRF, you're able to be significantly more accommodating than that 4-pipe hydronic, but it's very similar in the way it's going to change over. So just quickly, we're going to look at the different types of equipment used for the 2-pipe heat pump system. We're going to start from the left, moving on over to the right. It's actually a very simple system. So you're going to have your compressorized condensing unit. Now that unit can either be an air source condensing unit, like we're going to see here on the top. That unit is going to typically be placed outside, although that is not always the case. We leave out pictures of your headers and branches and joints because that's really just going to be your flexible refrigerant line set. And then you're going to have an indoor unit. We have a variety of indoor units, which we'll kind of touch on all the different types later on in the presentation. But what you have to kind of think of is that's the unit or the piece of equipment that is going to be serving each individual space or group of spaces that are all going to be connected together. The last component to the heat pump system is going to be some sort of system control. That can be either a thermostat, like you see here on the right-hand side. We have a simple thermostat up top. You move down into a little bit more of a localized controller thermostat, second down from the bottom, and then all the way on the bottom you have that's an image representing either your central controller or your BMS system on a larger scale commercial project. I'd like to note that we kind of touched on the air side or air source condensing unit that we show on the top. We also have a full line of water source condensing units. While that is not usually a super widely seen application, it is something that in Japan, China, and Europe is extremely common because of how efficient it is, and they are also significantly smaller than your typical air source condensing unit. So if you have any projects that you may be working on where there is an existing water loop, or you're really, really tight on space, a lot of times a water source system can really help in accommodating servicing that application. One thing to touch on with the heat pump system and VRF in general is that you can overconnect these systems. So it is not going to be just simply, you have a 3-ton load, you have a 3-ton condensing unit and a 3-ton air handler. You can actually go up on a heat pump system all the way to 130% of connected capacity. So what this allows for you to do is say how we kind of discussed earlier that each zone is not going to be a constant load. Basically, you're taking advantage of the diversity in the space and realizing that not every single space is going to be asking for 100% at every given time. So you can recycle some of that unused energy and send it somewhere else. So you can actually, connect 13 tons of HVAC or 13 tons of indoor unit to any given condensing unit that is going to be a heat pump. So the second type of technology we have here is called heat recovery technology. Now, I know it looks very, very similar to the heat pump technology that we saw just a few slides ago, and that is actually the case. It is very, very similar, except for one component that is actually called out on this picture above. That's going to be our branch controller. So you're going to see that we still have the outdoor unit, all of your flexible refrigerant piping. You have all of your indoor units serving their individualized zones, but the one additional component there is that BC you see in the top of that picture. So the way we like to think about the BC controller in simplest terms is really it's just a traffic cop. So what it's going to be doing is it's basically a component that's added to the system. It's full of sensors, linear expansion valves, and diverting valves. So what it allows us to do is move energy from zones in cooling to zones in heating without using the outdoor unit. So it's important to realize, and I don't know if this is something that everyone knows about, so I'm going to touch on it quickly, that when you're cooling a zone, you're not necessarily providing cooling to that space, you're removing heat. So when that refrigerant goes into your zone in cooling, it's going to be absorbing all of the heat in that space, and typically you'd send it out to your condensing unit, and all of that energy would be dispersed into the atmosphere. So what the BC controller actually does is it allows us to take all of that waste energy from zones in cooling and divert it as hot refrigerant over to zones in heating. It's going to allow you to, we call it free heat or energy recovery in this instance. So let's see if this slide actually has, it does not. I thought there was a little bit of a picture to show you guys, but I do know that's coming up a little bit later down the line. So again, this is just breaking down the individualized components of the system, and you can see that they are really, truly almost identical. The main difference going to be that BC controller. So again, you're going to have your compressorized condensing unit, whether that be an air source unit as you see on top there, or a water source unit like you might see on the bottom. Both are extremely flexible as far as their installation goes. Water source units are slightly smaller, but we do have a greater variety of those air source condensing units. So this is something where hopefully I can be of value to all you guys. If you ever have a question on an application, let me know, and we can kind of move forward on that. But just moving along, the BC controller is what we talked about being that traffic cop. That's going to be full. You can see all of those ports. This is our 16-port model. That's going to be there to divert all of that refrigerant from zones of cooling, zones requiring heating. And basically, one thing to kind of think about in these, and I'm going to actually take 1 second to go a slide backwards. Let's see, will it show? Here we go. So this is actually showing your absolute perfect kind of application where you're going to have a totally balanced load. So if you have your 4 zones over here in cooling and 4 zones requiring heating of a similar load profile, this is actually going to allow that condensing unit to work at exactly 50%. This is one of the reasons that VRF technology can really be so efficient, and we're going to touch on some of the compressor information in a few minutes, but this is really what's going to allow you to really kind of beat all of the new efficiency legislation that's coming out and really kind of surpass all of the competitive HVAC technologies as far as efficiency goes. When you're designing for a heat recovery system or an R2 system, if you're looking at a Mitsubishi product, we really try and balance the load diversity exactly, or as exact as possible. So one thing to kind of consider is if you're going with a heat pump, you might want to service an entire facade of a building or an entire building in and of itself. Anywhere that you might think a load profile is going to be very similar. We like to look at kind of vertical applications for heat pump, whereas with heat recovery, as you're going to see in this slide, we like a horizontal application. So you might be servicing, the eastern and the western facades of a building, really maximizing your load diversity in that space and allowing as much heat recovery as possible to occur to really kind of save your compressor from doing any extra work, anything that it doesn't need to do. So back here, Again, we have all of these same indoor units and outdoor units on both the air and water side for both heat pump and heat recovery technologies. Really, the only added ingredient is going to be that BC controller, and the control system is going to act identically. So you can have this system controlled by local thermostats, either a smart thermostat, as you see in that second one down, or that localized or centralized controller tied into your BMS system. So this next slide here, we're going to start talking about the differences in compressor between a conventional HVAC system and a VRF HVAC system. So I'm sure most of you guys are familiar with the way a compressor on a traditional system or a conventional compressor would work. It's on-off compressor control only. So this slide right here is actually showing linearly, the temperature in the space. We have a set temperature we're trying to achieve of 75 degrees Fahrenheit. We're actually going to start off at that 90 degrees, in the space. This may be, coming back after a long hot summer weekend, something like that. But when you're trying to get to that 75 degree set point, what's going to happen with your conventional compressor is that it's going to kick on to full power, 60 hertz, as it's going to, draw all of that energy in to start cooling that space as quickly as possible. Unfortunately, because you have such a long way you're trying to drop that temperature, it's going to take a long time to bring down from 90 degrees all the way to that 73 degrees set point, or actually 2 degrees below deadband where it's going to try to go. So once it does hit that 72 or 73 degree set point, your compressor is actually going to turn off. That's traditional compressor technology. That's how it's always worked in VRF systems. I'm sorry, in HVAC systems for kind of time immemorial. So once you reach the 77 degree deadband, which is coming up over that 75, you're going to kick back on. This cycle is going to repeat itself, and I'm sure you guys have dealt with what we call hunting. It's basically just the space between those two deadbands that the system is allowing the temperature to fluctuate before kicking on or turning off the compressor. This is kind of a horribly inefficient way of doing things. Some mainstream or rooftop unit systems, HVAC systems, have moved towards a more kind of modulated control, but we don't see it very often. And that's actually the exact kind of control that Mitsubishi VRF is going to use. So we use an inverter compressor. And one of the main differences is that we don't actually have to, with an inverter compressor, adhere to that strict 60 hertz limit on the top end of our compressor scrolling. So what we can actually do when we have the call for on, we start off at a very low level, very low amp draw. And this is the same of all VRF systems. You're going to bring in a very low amp draw immediately and then turn it on to super high gear. We go all the way up to about 130 hertz, which is allowing VRF Technologies to drop the temperature from whatever set point it may be. In this instance, it's 90 degrees Fahrenheit. You're able to drop all the way down to that 75 degree temperature very quickly. This is really just due to the extremely high rotational speeds on inverter compressors as opposed to more traditional compressors. And then what we're going to do once we hit that set point, we don't turn our compressor off almost ever. So what this allows us to do is modulate that compressor, not go with the typical on-off control, and actually hug that set point significantly more closely. Because you're not kicking on, kicking off, you can keep a deadband of half a degree above or below that 75 degree set point, and really modulate to keep the control in the space, keep the temperature in the space very tight. So what I kind of like to think of this as is, your original compressor would be kind of like driving in city traffic. You're driving either full on, full off, you get to your red light. Everyone knows that in your car driving in the city, you're driving in a lot of traffic, you lose a lot of efficiency, your miles per gallon go down significantly. With the inverter compressor that's going to be used in VRF technology, this is a lot more similar to driving on a highway, putting it into cruise control. So once you get to your set point of 75 degrees, as we see here, you're really just scaling back and only giving the amount of energy to that compressor that it needs to maintain that set point. You're not letting the set point fall and chasing back up, or letting the set point rise above and chasing back down. You're purely maintaining what you get, and that's a lot more it's a lot easier on the compressor, and it actually allows the compressor to last significantly longer than your traditional compressor. So moving forward here, we're actually getting into a little bit of applications-based information for VRF. So this is a nice little diagram just saying, how do you turn your lights on when you go home? You walk into your house, you might walk into your foyer, you're gonna turn the lights on there, maybe in the hallway serving all the rooms of the house. And I'm gonna skip forward a little bit, but I think you guys get the picture. You're only going to be turning the lights on in the space that you're using. It makes no sense to have one switch for your entire house, turn all of the lights on or turn all of them off. I mean, I know growing up, I always got in trouble if I turned on or left on lights in the space that I wasn't in. That's very similar to how we kind of look at using your VRF systems and AC in general. So how do you turn your AC on typically in a house or any kind of application that you might see? You walk in, there's going to be one centralized thermostat in the foyer, and then you're going to cool or heat that entire space to a single set point when very typically you're not going to be using almost all of it. So why would we do this? It makes no sense. Realistically, as we spoke about earlier, as I was telling you earlier, there's a lot of kind of new legislation coming in specifically in New York City with Local Law 97. That's going to make energy usage and carbon emissions, we're going to have to adhere to some significantly more stringent guidelines, and just blatantly overcooling or overheating a space is not going to be effective. And it's really not going to help us maintain carbon emissions as we get into kind of 2030 and 2035 and move beyond that. So the solution here is a zoned application. This is calling for a zoned home with VRF. But realistically, we can talk about any kind of application would be serviced in this same manner. So what we're going to do is, and I'm going to kind of fast forward through some of this here for you guys, but what the point I really want to hammer home is that each individual zone can be turned on or turned off to a different set point and only provide a specific amount of heating or cooling that is going to be required for that space. So as you can see, your foyer, your storage area, and your bathroom, those are going to be probably somewhat underutilized zones. You're not going to need to cool those, and typically in an application like this, I would see those typically being off or at least really ramped down to where they're not going to be serviced all that much. I know typically a lot of times bathrooms and storage rooms are not even provided with heating or cooling, which is kind of, in this, we're showing that they are going to have their indoor units, but I would assume that those units are going to be pretty underutilized. Then you can go into your master bedroom, serve that bathroom and a walk-in closet off of a single unit. But really what we're looking at here is that each of these individual zones is going to be kind of working to its own set point and only providing a specified amount of heating or cooling. That's really the main takeaway for VRF technology in general is its efficiency through zoning. So we always want to think about how many independent zones can we service, and we do that because we want to only serve the zones that are going to be most prominently used while turning off the zones that are not going to be used or rarely used. So that's what we kind of are talking about when we're talking about diversity. And if this was a heat recovery system, that would be even better. This would really allow you to take the zones that are not being used at all, recover some of the heat or the latent energy in those spaces, and serve some of the other spaces, making the efficiency even more significant. All right, so in the marketplace today, there are two different main types of VRF technology. There's going to be a two-pipe heat recovery system. That kind of represents Mitsubishi and a couple of our other similar manufacturers. There's also a three-pipe system. That's going to be representative of some of the other manufacturers in the market. And this is actually the way Mitsubishi used to do things. I would say it's probably the most common type of VRF system today. Really, the only thing we want to take a look at here is the total connections. So total connections, kind of the way we like to look at it, and I know a lot of the other manufacturers in the market look at it, is really any connection point is a possible point of failure. It's something that the manufacturer really doesn't have very much control over. That's where you're going to see, most of the time, There's really not very many kind of leaks or defects with the units themselves. It's when the units get installed, there's going to be likelihood or not even possibility of failure at the connection point. When you're looking at a two-pipe system, this is a heat recovery system we're looking at here with your outdoor unit, your BC controller, and all of your 4 zones served on the indoor units. You're going to have connections at the BC controller and only the BC controller to the indoor units. That's going to give you a total of 20 connections on a two-pipe system. The same system actually with 3-pipe connections and individualized distribution boxes to each of the various 4 indoor units that are going to be serving the spaces. Really, that's just going to be, it's going to exceed the amount of connections. We show 58 here. That's just really on a 4 indoor unit system. It's obviously going to be amplified as the system kind of grows in size. But the one thing we just want to think about is really just minimize your amount of connections that are going to be, field connected. That's really just the only point of failure that we like to really kind of think about with the VRF system. And just something to kind of keep in mind moving forward. So integrated controls, I'm not going to really get too deep into this and bore you guys with a lot of in the weeds details, but one thing that I really want to highlight for everybody is that VRF systems are extremely flexible with the type of control that they can either accept or output. So like we said earlier, VRF can be controlled by, as something as simple as a standard on the wall thermostat that can control, most of your typical VRF systems, whether they're residential or whether they're a large commercial system. But obviously, once we start getting into the larger, more commercial systems, we see the need for building management systems and integration into stuff like BACnet, lawn works, third-party equipment control, or tenant billing applications. One thing that I will say without getting too manufacturer-centric is that VRF technology is capable of completing all of these. So if you do have an application where you're looking to tie into a BMS, or you're looking to integrate the VRF system with a bunch of third-party equipment, that is not going to be an issue. Also, tenant billing. This is something that VRF is actually very, very good at accomplishing. A lot of manufacturers on the market have the ability to go into a tenant billing kind of application. It's actually really good if you're going to be serving a bunch of individualized apartments. Most VRF manufacturers do have the ability to kind of break down energy usage by apartment and individually bill those tenants, typically with a third-party billing agency. So now we're just going to touch on a typical day, and this is going to be showing you the value of the heat recovery system as we kind of discussed earlier. So let's consider this a typical fall day here. We're actually going to be, this is building startup. This is early in the morning. We're going to be in 100% heating mode. We're really going to be trying to heat that space up to an acceptable temperature for everyone to come in and kind of start working. So that zone, or I'm sorry, this application is going to be 100% heating early in the morning. As the day moves on, we get 9 a.m. Everyone is kind of coming into the office. We have that eastern facing facade over here. That zone, because of the solar load that's going to be coming into it, is going to be heating up a lot more quickly than the other zones in the spaces. So what that BC controller over there is going to allow us to do is, provide cooling to those zones, but allow the other zones that are not yet kind of up to set temperature, maintain their heating, stay in heating mode. So then the day is moving along a little bit further. We might have a 12-person meeting in the conference room, some kind of board meeting, anything like that. That zone, because of the the load in that space, is also going to require cooling. And this is actually going to be an ideal kind of scenario for our heat recovery, as we discussed earlier. We're kind of showing the 4 zones, the 3 on the eastern facing facade and the 1 conference room, all requiring that cooling, and the kind of more central zones in the middle of the building that don't see a lot of solar load or any kind of other load, they're going to still be in heating mode. This is going to allow that condensing unit to ramp down all the way to 50% and only provide enough energy to cool the spaces down that are going to require cooling. then recycle that energy into the spaces that are going to need heating. So this is actually what we call free heat. That's kind of a typical term you guys are going to hear when you deal with VRF in the HVAC marketplace. And this is typically just, as I was saying, a function of recovering all of that waste energy from the zones that are going to be providing cooling and redirecting them through a BC controller of some kind or a controller of some kind into the zones requiring heating. So in the afternoon, as the day heats up, all of these zones are going to be requiring cooling, and that's actually completely acceptable on a heat recovery system. That's one thing that I do want to stress. If you guys do go out and start designing around VRF and you do start using heat recovery, maybe to meet some of the efficiency standards that are coming into the market, or just because you kind of find it good for that application, heat recovery is able to act as a heat pump. So all of your zones can be in either heating or cooling, but the main difference with that heat recovery is that it's going to allow you to each individual zone is going to be able to go into either heating or cooling on demand. So really, it's very similar to the heat pump technology that we discussed earlier. The only difference is that each zone can then transfer into heating or cooling as needed. So this is something as a mainly architecture presentation that you guys are definitely going to be more interested in. VRF is extremely flexible with its installation, and is very much so less intrusive to existing architecture if you guys are working on any kind of landmark project, or even in just New York City, where a lot of the applications are going to have a lot of really tight kind of windows that you're going to need to fit heating and cooling into. I know that I've actually worked and kind of sold for other HVAC manufacturers in the past, and I have dealt with a lot of nightmare scenarios where we're looking to bring in heating or cooling to a space, but we really have a lot of kind of difficulty getting there because of either ductwork constrictions or where we're going to put the equipment and how we're going to connect it to that space. One of the main advantages with VRF is that you're kind of able to skirt around this because of how flexible the installation actually is. That's one, because in most cases, we're going to be running small refrigerant piping instead of large ductwork to the space. We're going to touch on that in a couple minutes, just see exactly the difference between the piping and the ductwork. And we also have a significant amount of outdoor unit installation flexibility. One, because our outdoor units are modular, and two, because they can really be placed almost anywhere. There is a lot of flexibility with the refrigerant line set as to where you can put these units. I've actually worked on a lot of residential projects where the customer may not want to see the outdoor unit, and we are able to hide it all the way behind a barn or a garage somewhere on the property, dig the refrigerant line underground, run it a significant distance into the house, and have no operational issues. So really the flexibility of the VRF installation is one thing that I want to really stress to you guys. It's a main advantage over a lot of typical HVAC technologies. So we think about, how is this possible? How is it possible that VRF can really be so much more flexible than a lot of the more typical technologies? We'll look here at a scenario where we're trying to deliver 20 tons of cooling to a space. So you can see that with your typical kind of if you're using ductwork to push air from a rooftop unit, you're going to need 30-inch diameter ductwork, or the equivalent in a rectangular, whatever that may be. That is a large, at least a main duct run that you can branch off of. But bringing that into a space can oftentimes be difficult. If you're going with a hydronic system, you're going to have at least 4 pipes to provide heating and cooling. You're going to have your 2.5-inch iron and your 2-inch iron on the heating side. And then once you get all the way down to the VRF, you can see here on the bottom right, the largest piping that you're going to have on a VRF system is going to be 2 1/1/8-inch copper pipes coming from your outdoor unit to your indoor units. You can branch off of those directly. So you really save a lot of space, especially once we start looking into insulating the pipes. And even once we kind of look at the ductwork again, this, I want to stress, is obviously, as you guys are watching it on your computers, it is not life size, but it is to scale. So if you take a look at this, this actually gives a pretty valid representation of the size difference between your air duct work, your water piping on a 4-pipe hydronic system, and your 2 pipes coming from your VRF system. Now, it seems kind of counterintuitive that you can provide that same 20 tons of cooling or heating to a space with such a small amount of piping as opposed to the larger piping on the hydronic system, and also the very large ductwork coming in off of your typical rooftop unit or something like that. And we're going to look at how that's actually possible. Really, the main reason is because refrigerant is just so significantly more efficient at transferring energy than the other modes such as air or water. So if we're looking at a typical air system, this is getting a little bit into the enthalpy side of things, but air can transfer about a half BTU per pound of air at any given time. So if you're looking at the same thing on a water side, you almost get 9 BTUs per pound of water. So you're considered about 20 times more efficient going from air to water. And when you go all the way down to refrigerant, as we show on the bottom, you can transfer 85 BTUs per pound of refrigerant. So you even go 10 times more efficient than water once you go to refrigerant. And that's why you can provide such a large amount of heating or cooling to any given space with such a small refrigerant piping run. It's just really a factor of kind of physics and the ability to transfer as much energy as possible through as small of a medium as possible. This also ties a lot into VRF equipment weight savings. So your typical VRF system is going to, on an outdoor unit kind of looking basis, going to be about 70 pounds per ton. That's when we're taking into account, your 10-ton outdoor unit is going to weigh about 700 pounds. Average equipment weight cost on a kind of pound per pound basis on a water-cooled chiller is about 101 pounds per ton. So you're going to see approximately a 31% reduction in equipment weight. So while that's good in and of itself, really the main difference that we're going to see is the weight reduction and the role it's going to play in being able to reduce the actual structural support needed to support the condensing units. So one thing that we see a lot in New York City, I know, I go up onto roofs and I see a lot of these really giant rooftop units, whether they be modular or custom air handlers or something like that. You might have a 200-ton rooftop unit serving a building, and all of the weight for that rooftop unit, all of the weight for that cooling and heating provided is going to be in a centralized location. One thing that I touched on earlier a little bit is that with VRF, you're actually able to kind of split out that weight and provide multiple systems to serve the building. So for example, rather than having a giant, rooftop unit sitting in a centralized location on your roof, you can have, 5 different smaller rooftop units with VRF, positioned out towards the corners or in areas that there's already dunnage or already existing structural support. And in a lot of cases, it's really able to minimize the amount of retrofit support you're going to have to add to a project. That's going to, save on installation costs. That's going to save, kind of just on total project costs. And that's one of the main drivers of VRF over a lot of traditional systems as well. Moving along, I know a lot of applications that I see is conversions or retrofits from these traditional chiller boiler systems. One thing, it's weight. They're about 30% heavier, but they're also significantly larger. And as I said earlier, need to be centrally located. So one thing that we see is when you're able to split out the kind of total load and kind of move around your condensing units to where it's most advantageous for the building, you can reclaim a lot of mechanical space that is typically used, for that existing chiller boiler system and repurpose that into something that the building owner can actually monetize. So rather than having this, massive chiller boiler plant in a building, you can eliminate that, go with an air source or a water source VRF system, and then retrofit that into any kind of amenity space that might be valuable to that owner. We see a lot of times them being retrofitted into gyms, if it's a kind of mixed use space, you can retrofit that into something that's going to be more acceptable for shopping or whatever it may be. But really, you're just reclaiming the space for the owner and allowing them to either, break even on the cost of that space or monetize that space rather than using it as something where they're going to have to be spending money. So just moving along with installation flexibility, this is just showing, these are kind of outlines of Mitsubishi units being rigged onto a roof. One of the main points is that these units are modular, as you see, and almost every single module VRF system kind of, manufacturer irregardless, can be fit into your standard freight elevator or easily rigged onto a roof. Rather than having to go through the trouble of doing these massive rigging projects where we're, going through, weeks and weeks and weeks of having cranes on a job site, typically your VRF systems can be brought in significantly easier and at a significantly lower cost to the owner or whoever may be paying for that project. One thing that I really do like to show is the installation of the condensing unit inside. This is one of the unique advantages of a VRF system. So this is actually in the Mitsubishi office over on 7th Ave. If you guys ever want to come see it, you are more than welcome to. But this is actually the condensing unit that is serving the majority of the office space that I personally work in. We were able to install this unit inside, as is typical with a lot of applications. Basically, what you're able to do is, as long as you're introducing fresh air to the Mitsubishi condensing unit and ducting it out of the space, you're really able to kind of put it almost anywhere within the building that you can spare a little bit of mechanical space, and that unit will act as if it is completely outside. It won't see any derating, it won't see any kind of issues with performance. So this just ties in a little bit more into the flexibility of installation that we discussed kind of throughout these last couple slides. You can reclaim that chiller boiler space and not, have to use that in a way that's going to be providing heat and cooling to the space, because you're able to move your condensing units into kind of smaller, individualized zones, and that kind of goes into zoning the space again. This unit itself is actually serving a couple spaces, and this is what we kind of like to see in a lot of applications, where multiple floors are going to be serviced. Just to show another kind of application where this works, this is actually turning a small kind of soffit in a kitchen into a kind of makeshift mechanical room. And, as long as that soffit is going to be insulated and you're able to provide the same amount of makeup CFM that unit is exhausting, that is a completely acceptable application. There's very little need to provide a lot of service space around these units, especially if you're putting them inside, which makes, again, just installation extremely, extremely flexible. So now moving right along, we're kind of going to pass a lot of the application side of things, and I'm just going to touch on, for the end of the presentation, a lot of the different kinds of indoor units that most VRF manufacturers have to offer. So the first and the most common unit that you're going to see is that wall-mounted unit. I know probably the most common application of VRF in America right now is the wall-mounted unit. That also goes for worldwide. While we really do know it is not the most aesthetically pleasing unit, it is by far the quietest and most efficient. So if you're dealing with an application where the owner is okay with the wall-mounted unit, the installation flexibility is great, and the efficiency is really off the charts. Then moving kind of to the right one, we have the ceiling suspended unit. This is a very common type of VRF unit that you're going to see. This is very similar to your wall-mounted unit, the only difference being a slightly larger fan, which allows for a significantly further air throw to a space. Really application specific when you might be seeing these. I see these a lot in restaurants and bars. Really just application specific, but the main thing to take away from a unit like that is the air throw that you're going to be able to provide. Thirdly, we have the floor standing unit. This is really a great plug and play replacement for anywhere that would have a traditional floor standing 4-pipe hydronic heat pump. Most of the retrofits we do on hydronic systems, we see a lot of these floor standing units. Typically institutional buildings, schools, hospitals, things of that nature. These are really a great plug and play replacement because they're built to almost the exact same specifications and kind of size as a lot of traditional hydronic systems indoor units would be. So this is just a little bit of a joke on ourselves. This is our little architect up top screaming because he knows he does not like the look of that wall-mounted indoor unit. But hey, that is again going to be your quietest, most efficient option there. So just something to think about. Very good for installation flexibility, very good for efficiency and sound levels. So moving on, this is going into more of the VRF ducted offering. So while we typically are known for a lot of the non-ducted options, that's kind of something that's pushed in a lot of the literature and also a lot of existing installations. We also have a very kind of large variety of ducted indoor units that are available to use as well. So we have our typical medium static ducted unit, low profile ducted unit for anywhere that's going to have some significant issues with height or installation flexibility. We also have that vertical ducted unit, which is a great, again, plug and play replacement for most of your kind of hotel spaces or anywhere where you're going to have that vertical installation. One good thing to know about almost all VRF vertical ducted units is that they can be installed horizontally as well. They are truly a multiple position unit. So that's one thing to take into account. They're great when you have a ducted application. You need a little bit more static pressure to overcome long duct runs or anything like that. They're a very good option. This is just a picture here showing the floor-mounted vertical air handler in its typical application. I'm not going to get too much into this with you guys, but just one thing to remember: it can be mounted either way, left, right, up or down discharge. So it's extremely flexible as far as the installation goes. There's also ceiling recessed cassette units. These units are very common as well. Typically, we have our 2x2 and our 3x3 options. The 2x2 fits directly into ceiling T-grid if that's already available on a project. This is a very nice plug and play kind of installation option. Moving on, you can see on the picture here on the left, this is a 3x3 unit. Typically, you're going to see those installed into a hard ceiling. The one difference between the 2x2 and the 3x3 is that the 3x3 is going to need an access panel on the right-hand side of the unit, or realistically, on the side of the unit that has that control box you can see in the top picture. Once you have that access, you can really service this unit totally. So that's just one thing to think about. Lastly, here on the bottom, we also have that one-way cassette unit. This is a unit that's not seen as much, but it's something that's very valuable to VRF manufacturers. This is great for installations where you may want to wash windows, or in the case if you ever have to fit between two 16-inch on center ceiling joists for a residential application, these units are designed to fit in there exactly. So that's a really nice application for residential projects. So just quickly, and I know we're running a little bit short on time here, I'm just going to cover all of the units right here that you're going to see can accept outdoor air. So these are units that have ventilation capabilities. With the new Local Law 97 kind of codes that are really the group of codes that's been passed into New York City law recently, there's also a new economizer code, which is going to require a lot of VRF units to accept, or really a lot of indoor units to accept ventilation. So these are all of the units that most typical manufacturers can provide that are going to be able to accept ventilation. Really, the only units that are not capable of accepting ventilation are going to be the standard wall-mounted unit and that the similar unit that is going to have a really good air throw. So just next here, we're going to get into refrigerant piping flexibility. I'm not going to go through all of these numbers here for you guys, just to maintain a little bit of time for questions. But one thing to know is that with your typical air-cooled system, you have over 3,000 feet of refrigerant pipe that you can run for that system. With your typical water system, you're almost at 2,500 feet of refrigerant piping. These numbers have actually been updated slightly on the piping height difference. But for now, we'll just say that if your outdoor unit is higher than your indoor units, you have 164 feet of vertical separation capability. And if your outdoor unit is going to be lower than your indoor unit, you have 131 feet. Realistically, that's just a function of working with gravity. If your outdoor unit is going to be higher than your indoor unit, you have the ability to kind of cycle that refrigerant up using the gravitational forces to kind of pressurize your return line. You don't have that advantage when you're working with the outdoor unit lower than your indoor unit. But really the main takeaway for this slide is going to be almost any project, regardless of how large, installation of refrigerant piping is not going to be an issue. Lastly, what does quiet sound like? So, how loud is a traditional HVAC unit? And we have our dB scale right here, and you can see, you know, you have your standard PTAC unit. I'm sure most of you guys have stayed in a hotel room with one of these. These are going to be about 50 to 60 dBs when operating at 100% capacity. That's about as loud as your typical residential condensing unit that you would see on many homes. Those are both going to be in that 60 to 50 to 75 dB ratio. When we start getting to larger, kind of more commercial projects, where you have your air-cooled chillers, those go all the way up to 85 dBs per module, so they get extremely loud. They can almost be like standing next to a plane that's taking off. When you get into VRF systems, they are extremely quiet. That is one of the things that is very nice about them. And I'm not going to draw this out too much, but one thing that I really like to show is that the commercial outdoor unit in its single module, when it's running at 100% capacity, which we shouldn't be designing for, typically we want them to run somewhere between 50 and 75%, but when it's running at 100% capacity, the outdoor unit is going to be about as loud as your standard PTAC. So just really the parallel to draw is most people are okay sleeping with that PTAC in a hotel room. That's as loud as your outdoor unit is going to be. So that's why you can install those inside without any sound issues, without any vibration issues, anything like that. As you can see, as the condensing units get smaller, they get quieter. Specifically the residential units or the lower capacity units. Even the loudest indoor unit you would see here is our ducted unit. That's going to be somewhere in the 23 dB range, so extremely quiet. And again, the wall-mounted indoor unit really comes in on top. Efficiency, installation flexibility, and also sound. It's operating at 100% all the way down at 19 dBs, which is actually quiet enough to be operated in a sound studio without kind of ruining any recording or anything like that. So that's just a nice piece of information for you guys. And I appreciate you guys listening to me through this whole presentation. But that is actually the end, and that concludes the AIA presentation for today. So I'd like to open it back up to Andreas if he's handling the questions, and if you guys have anything you'd like me to follow up on, now is the time.
Thanks, Alec, for the fantastic presentation. There was a lot of very good information. We have, as you could imagine, many questions in the chat box.
Fantastic.
We have Caleb with us, Grafford, a New York Pacific board member, who will kind of facilitate those questions. One question I had just to get started, what is the smallest indoor unit, for heating cooling load you offer? And are you working on even smaller ones, since in the past, of course, we typically see very small heating and cooling loads?
Absolutely. So as of now, we have indoor units that can, on the top end, go all the way up to 4.5 tons for any single indoor unit. And we actually have, with Passive House in mind, Mitsubishi, I can only speak for us, has just released 2 new wall-mounted and cassette-style indoor units that go all the way down to 4 MVH. So that's something that we see quite a bit, and Mitsubishi has done a good deal of Passive House work in the past. We see those really small heating loads. So the new introductions of these 4 MVH units is really something that we're looking forward to and hoping we can capitalize on for Passive House applications.
So Caleb, maybe you take some of the questions there.
Yeah, in the chat, like obviously in time of COVID, indoor air quality was like one of the first questions. And
Sure.
I don't know if Robert Fahrenbach can unmute himself, because he's used a lot of initialisms that I don't know. But it's like, can one install BPI, UVCC, PCO, ESP? I don't know what any of the flows except for the UVC are into an indoor air unit.
Yep.
Right? Because obviously we're recycling indoor air. We want to think about how we could potentially, or if we can increase filtration, that kind of thing.
Of course. So I know with a lot of the new regulations that are going to be put in place, a minimum of a MERV 13 filter is going to be needed just to get things open and running. So while VRF systems are not known for their like really robust external static pressure capabilities, all of our ducted units actually can be modified. Well, they can have a MERV 13 filter added on with no issues as far as operation goes. Most of those units are operating between 0.7 and an inch of static pressure, which is more than enough to handle your standard MERV 13 filter. As far as the UV goes, I've actually worked on a couple applications very recently where I am using UV in tandem with the ducted units again. UV is kind of difficult when you start moving into the cassette units or the wall-mounted units. You can use the UV light in like a plenum that you would see before those cassette units or serving the room that the wall-mounted unit is located in. But if you're going with a ducted unit, you can actually tie in the UVC to the control board of the ducted unit. And what that allows you to do is anytime the ducted unit kicks on, you can call for that UVC lighting or whatever kind of purification device you're using to kick on as well. So we do have the capability to control a third-party UV light or something that's going to be cleaning the duct in tandem with the ducted indoor unit.
Let's see. There's with any of the indoor units, there were a number of questions about outdoor air supply, right?
Yep.
And and it's a general question, but I think it bears telling the audience that may not be totally familiar with the material.
Sure. So all of the Mitsubishi indoor units, other than the wall-mounted unit, can accept outdoor air. So they're going to have various CFM ranges of outdoor air that they can accept. But the main rule that we like to stress is that, regardless of how much outdoor air you're going to be providing to the unit, we only want to see at maximum at any point 20% raw outdoor air. So once you start exceeding that 20% of total indoor unit CFM threshold, we prefer that air to have some kind of preheating typically, just so that unit isn't taking in, 100%, 5-degree outdoor air in the dead of winter in New York City. We want to see that air tempered a little bit so that the indoor unit can actually, really, because they're rated at around 59 degrees. So if you can bring up your outdoor air to about 59 degrees before entering that indoor unit, no problem with operation.
And so with that indoor installation that you did, how did you do? I mean, basically, if you're passive house, you're trying to look at some form of energy recovery ventilation. And yep. I was going to ask a question whether you can do an indoor installation, and you beat me to it with your slides. So, but
oh yeah,
what do you guys do for your ventilation air on that installation?
So you're saying for the installation of the condensing unit inside?
Yes, in your offices.
Perfect. So what we actually do with that is the best way to do it is to have it, we're lucky enough that we have a louvered wall on that side of the building. So we were actually able to include just that louver so you can duct the air out of the space. And we just have a simple fan bringing in the exact amount of CFM that unit is exhausting from the space to maintain a neutral kind of, occupancy in there. So really, as long as you're bringing in the same amount of CFM from outside that the unit is exhausting, it's going to act in the exact same way that it would if it was placed outside. You don't have to do anything.
But usually in conventional air conditioning systems installed into, say, like loft buildings in New York City, which is a pretty common installation, there is an economizer would have been put on and
Yes.
You would have been in a certain amount of outdoor air as a typical situation. And in your case, what did you do for that ventilation air?
Oh, okay, understood. So you do not need to service that condensing unit with economizer, but for ventilation air for the rest of the space, Mitsubishi does have a line of indoor ERVs that we were able to use. So that is something I didn't want to bring up to become too manufacturer centric, but there is a lot of, we have a partnership with a company called Losnay and can provide ventilation air with an ERV mounted inside from anywhere from 300 up to 1200 TFM. So we have 2 of those in the office as well.
Okay, yeah, that was sort of what I was trying to get at. There were a number of questions about excess heat diversion. One person, Howard, asked if it could be diverted to an ERV. I wanted to know whether it could be diverted to, say, a domestic hot water preheat, like in multifamily.
Sure.
And is it possible with a water system to recover heat from wastewater? And whether you're working on anything like that?
Yes. Okay. So I'll start from the beginning of this. Is it possible to recover heat to an ERV? Yes. So it is possible, but it would not be directly to a, so the way to think about it is the ERV is really going to be recovering that energy with some kind of energy recovery core. We can't supplement that core. But what we can do is provide heating and cooling or excess heat to a coil in the ERV if required. So we have the ability to provide, instead of an indoor unit, purely just a coil that can be placed in any kind of unit that you'd like. It can be placed in the ERV. It can be placed right into a duct run. So that would be the way I would recommend doing it if you're going to be supplementing an ERV, is to place that coil or refrigerant coil in the duct run prior to the ERV, so that you can preheat some of that outdoor air that might be coming in, or pre-cool some of that outdoor air that might be coming in either summer or winter, to ease the load that the ERV is actually trying to make up. So say you have 80-degree outdoor air and you're trying to kind of recover some of the cooling to allow that air to be circulated back into the space and ease the load on the system itself. If you can cool that air before it gets to the ERV, that would be the best way of going about that. So we can do it. It gets to be a little bit of an involved application, but it's definitely possible, not beyond the realms of things that are capable of doing. And then I apologize, what was the next one? You said domestic hot water?
Yep.
Okay.
Like particularly summer.
Yep. So we actually do have a domestic hot water unit. So again, trying to maintain kind of manufacturer agnosticism here, but Mitsubishi does offer a unit that actually cycles water through it, so we can provide domestic hot water with it. The indoor unit, instead of serving a space and heating or cooling, would provide hot water to the space.
Oh.
So we do have that, and that is typically they go up to 3 tons on an individualized indoor unit. But actually, within the next year, we are bringing over a product from Europe that can provide up to 2 million BTUs of commercial hot water to any space. So in the very near future, we will be able to use an air source condensing unit to heat all of the hot water needed for any size commercial application. It's actually, as I was saying, Europe, they're already kind of adhering to a lot of these strict kind of, energy codes. So they've already figured a lot of this stuff out. It's really just a function of bringing it over.
Yeah. There were quite a number of questions about refrigerant. The phase out of R410A, somebody said that R32 looks like it's the next one. I forget what the R is for carbon dioxide. Because it is a problem that leaks in refrigerant piping are probably void a lot of the efficiency gains, which somebody was noting in this. So maybe speak a little about that and whether you're looking at other forms of other media, like in supermarket installations for their coolers, that they're actually using some form of antifreeze, a liquid, as opposed to refrigerant. So whether, like, for these larger applications, you're like, what you guys are sort of thinking about and what you offer now.
Absolutely. So Mitsubishi is always kind of forward looking and kind of thinking about things like this. We are working on a bunch of products, and we actually do offer products in Europe and Asia that work on different refrigerants, not R410A like we offer in the United States. But the main answer that Mitsubishi is thinking about for the United States as it looks at some of the larger projects is we're moving towards an HVRF technology. So actually what that's going to be, and I don't want to spoil too much for everybody here, I don't have a release date on this, but within the next year, we should be able to provide a system that is only going to be refrigerant from the condensing unit to the BC controller. From the BC controller to the rest of the space is going to be water in the piping. So that really alleviates all of your ASHRAE 1534 issues. Right now, I know we have a lot of kind of, not really problems, but it takes a long time to engineer. I was just working with a customer of ours on a hospital space where you have really low RCL limits, and it gets very difficult with trying to kind of place units correctly so that RCL doesn't become an issue. But what the HVRF is going to allow us to do is overcome all of those issues. And on the other side, it's going to allow us to really, because you only have water serving most of the space, if and when a new refrigerant does come out that becomes the new standard, you're going to be able to just change out your condensing unit and leave the rest of the system. So, you know, if we have a new kind of refrigerant come about, we'll have a condensing unit answer for that refrigerant. It can serve that BC controller, and we'll make sure that you really only have to retrofit a small part of the system.
Would that be possible to retrofit an existing PTEC system in a building as well then, or?
Yeah, well, we can absolutely retrofit an existing PTEC system. Do you mean like on the water side without disconnecting existing piping? No, so really you would still need to run, you can pair off the existing water loop that you have with a water side condensing unit, and then have that unit tied into the new HVRF system when it is available. And then that would be able to replace the PTEC, yeah. But there would still be a significant amount of, you know, retrofit piping and things like that. It wouldn't be as simple as, you know, plug and play with a water side Mitsubishi heat pump right onto the existing water loop.
Smallest size of VRF actually was something I don't remember you actually hitting on. I know there's the S series, but I can't remember how far down that goes.
Yep. So the S series on the condensing unit side goes down to 3 tons. But we have condensing units that go into our M&P line. They go all the way down to 0.5 ton. Yep. And one thing I guess I should have mentioned earlier is when you're looking at a passive house application, one thing to take into account, the heat recovery system, not only is it more efficient, but when you're in the heat recovery system will allow you to shut off your unit. If a unit is not required to provide any heating in a space, you can actually 100% close down that unit so you're not getting any bleed through heat. So that's just something that oftentimes in these passive house applications, the bleed through heat is enough to actually heat the space because the package is so well kind of insulated. So it's just always something important to remember. If possible with a passive house, go with the heat recovery rather than a heat pump.
You mean heat recovery on your heat pump system?
So if you're going to be providing heating and cooling to the space, introducing that BC controller will allow you to 100% shut off. So if you have no BC controller, the indoor unit needs to leave its linear expansion valve like 2% open, just so that refrigerant can always be cycling through the system. With the BC controller, we have the diverting valves, which allows you to not have to deal with that. You can close off any given indoor unit to 0%, 100% shut off. So there's any hot refrigerant or cold refrigerant bleeding through even 2% of it through an indoor unit, which can affect in a really tight passive house, the load in the space.
Do you have kind of a very simplified cost number, how much more it costs, the heat recovery?
Sure. This is again, very much ballpark. Yeah. But if you're looking at your heat pump system and you're looking at a heat recovery system, you're going to be somewhere between 15 and 20% more expensive on the heat recovery side of things. However, you know, one thing to take in mind is that although it is more expensive on a, you know, installation side cost or equipment cost, your energy usage will be significantly lower. So your energy costs should be pretty well evened out.
And it's interesting because, I mean, it's hard to, since you guys are, since Mitsubishi is doing the presentation, it's sort of hard to sort of separate out into sort of like the higher conceptual level. And
Right.
in the interest of fairness, a lot of your competition is also working on a lot of the same issues that we've been talking about, but it is sort of like, it is, but at the same time, I mean, I think we've actually gone past our time, so I can ask, like, you know, what kind of engineering services do you guys present? Somebody wanted to know, like, how, you know, will you size systems, or what is the extent to which you provide technical support?
Sure. So for any architects out there, I'm actually for New York City and, you know, most of the, you know, mid-Atlantic area, the architectural lead. So I can help on any project where you're looking at design. I actually would provide a full system layout for you guys. It's something that I can't actually put the stamp on. Obviously, I'm not in a PE. But, you know, as far as taking it up to something that you would be able to submit to a PE, I can actually really do a full system design for any of the architects out there. That's really what Mitsubishi likes to provide, is full kind of technical support from, you know, as little as, you know, picking out an indoor unit to a full system design with a piping layout and an AutoCAD kind of system layout. That's, you know, something I can provide to anyone who's interested.
So, so with that said, I would like to thank Alec and Mitsubishi Electric for the very, very interesting presentation.
You guys.
We always, as the Passforce community, look forward to innovation to lower smaller units, more hidden, of course, and more efficient. That's very important to us as well.
Absolutely.
And so thanks for the presentation. Thanks, Caleb, for taking those questions at the end. And thanks, everyone, for joining our call today.
Yeah, good turnout today. We had like 86, which with the three of us, that's 83 people. So that was an excellent turnout.
Awesome. Thank you guys again. I appreciate the opportunity.